Hello ladies and gentlemen, and welcome to the next part of this episode. This is the last slide from the previous part, just to remind you where we got to.
Furthermore, it will be natural to assume that electrons fill these rings or shells from the lowest energy first and moving upwards, which predominantly is what occurs in nature and is known as Madelung's rule. Moreover, it is for this reason that we showed and explained to you that the 4s ring was closer to the nucleus than the 3d ring, since the electrons in nature fill 4s before 3d. The complete energy level order is shown in the second bullet point here. However, nature does not always follow this rule of filling the lowest energy first, and we've got three examples here. First of all, there is chromium, which has the same electron structure as argon, shown by the Ar in brackets, plus 1 electron in the 4s shell and 5 electrons within the 3d shell. However, if the lowest energy approach was taken, then chromium should have 2 electrons in the 4s shell, since this is a lower energy level than 3d, leaving only 4 electrons within the 3d shell. The reason though that chromium has the electron structure it does comes back to the ring structure that we mentioned a minute ago. Now, if we take the expected structure of chromium, then we would have 1 electron in the top 4s ring, another electron in the bottom 4s ring, and the last 4 electrons in the top 3d ring. In this arrangement, the top 3d ring is only missing 1 electron from being a complete ring. Furthermore, we've previously mentioned about this persistence property, which attracts threads of the same frequency together. And remember, all electrons are threads of the same frequency. Moreover, the more threads connected together, the greater the persistence attraction. Thus, when 4 electrons are in the 3d ring, their persistence not only connects them together, but is also strong enough to attract the lone electron from the top 4s ring. Hence, the electron leaves the top 4s ring and completes the 3d ring, leaving 1 electron in the bottom 4s ring, giving us the arrangement seen in nature. Moreover, if only 3 electrons are in the 3d ring, then their combined persistence is not strong enough to attract the 4s electron, and thus vanadium, the element before chromium, has the standard electron configuration. The same thing happens with copper, which by default would have 4 electrons in the bottom 3d ring. But again, these are strong enough to attract the electron from the bottom 4s ring, giving the configuration shown. If we look at the next row of elements, in particular niobium, then this time the energy difference between the 5s and 4d rings is smaller than the energy difference between the 4s and 3d rings. Thus, this time it only takes 3 4d electrons to attract the electron from the 5s ring, instead of the 4 that were required in the 3d ring to attract the 4s electron. Although we should point out that these electrons within the same rings cannot join together, as they all consist of the threads with negative poles, they are held together via this persistence in exactly the same way that the proton ring is held together. Therefore, overall, we have showed you that the nucleus's electromagnetic field produces funnels above and below itself, which exist much closer to the nucleus than the ring around the side of the nucleus. Moreover, that the electrons exist in rings that are situated in these funnels above and below the nucleus, with 1 ring from the top and 1 ring in the bottom, located at the same levels, forming an electron shell. Additionally, the electrons fill these rings from the lowest energy level first predominantly. However, if the rings are close enough in energy level terms, then the persistence of the electrons can attract lower energy electrons into higher energy rings to help complete the higher energy rings, as we discussed with chromium, copper and niobium. This has completed this set of videos, which have introduced you to this exciting new proposition, and we hope that you've enjoyed it. If you have any comments or questions, then please do ask using the comments section, and we will answer them for you. We will also be producing videos related to explicit parts of this research, which will include radioactivity, persistence, quantum mechanical spin, thermal and electrical conduction, and many more.
So I hope that you will actually join us for those videos, but if you'd like to know more information in the meantime, then please do visit our website at www.bowd-limited.co.uk. Lastly, please note that this proposition has not yet been accepted, so don't use it to answer exam questions. However, we would like to hear your views, opinions and questions regarding it, so thank you for watching.